I'm not sure if you can hear us, but I think we're having trouble hearing you on Zoom.
Just me.
Is that working for folks so far? For Zoom? After that camera restart? Might have to use the text. I restarted. Oh, Andrew says you can hear us. Thanks, Andrew. Anyone else having any weird issues at the moment? Okay, thanks again for mentioning that. I think what's going wrong with the chat, if you're curious, is I'm not even sure if you're in Zoom, you can see this bar right here. Anyone happen to know that if you've been through Zoom? Do you ever see that bar? Okay, that's a good thing to mention. Just for folks who are coming in through Zoom, let me show you what's kind of going on my side. Kind of the worst thing that ever happens is there's an update to Zoom, and that's exactly what happened. When I operate Zoom, you might not see it from my end, but there's a bar that looks like this. There it is. What that bar is supposed to do is it's supposed to hide down below on my taskbar. For one reason or another, it's not doing that. The reason that's bad for me is the way I find chats is it pops up and I know, oh, the bar is there. There must be a chat. But now it's permanently there. I'm going to just try to look down here at the very bottom by the red dot to see if a chat comes through. You might have to reset your chat a couple times. And for folks in Zoom, don't hesitate to say, hey, Mike, you've got a chat, or people in class as well. That's never considered rude. I might need a little bit of help. My strategy is breaking down over here. But I'm really glad that everyone can hear. So let's maybe, I'm not too sure for what point you might not have been hearing me. I'm going to assume the entire time class has been going. So just for a quick rundown of what we're doing on this one, or maybe even better, a quick rundown of the announcements. The major things I was saying is we're nearly done with section 4.1. After section 4.2, we're going to skip a section and be in section 4.4 on optimization. So it wouldn't be harmful if you read 4.3, but it's safely skippable. Then on this problem right here, this one I believe is pretty similar to the brand new quiz we're working on. Let me double check that. Quiz 8 is, yeah, closed interval method. It'll be based off that as a closed interval from 0 to 3. On the problem over here, find absolute maximum and minimum values of the function on its given domain. And what did I do? There it is. There's the closed interval right there, -1 to 4. So we're working on a problem that's similar to the quiz one. And the first thing we had to navigate was the product rule on this. Derivative of x went to 1. We copied e negative x squared. Then we copied x. And next, we're going to put the result of that derivative there. But we're sorting it out through the chain rule process on the upper right end. And this is about when I noticed no one could hear me on the Zoom side. Sorry about that, folks. Any questions at the moment, particularly for folks who couldn't hear me at all so far? Okay, thanks again for mentioning that. So let's now run through this derivative. We have to differentiate the outer function. Because it's an e to the x, its derivative looks like this, except it's a chain rule, so we don't want to put x, just a placeholder. Then we multiply by the derivative of whatever went in that placeholder. And that's when we pull in the inner function, negative x squared over 8. It'll go here and here. Now, it's done in this location. Parentheses are superfluous. They're just there to organize stuff. You can drop them right away. But on this one, we'll have to crank that derivative out. We get e negative x squared over 8 times negative 2x over 8. This derivative looks kind of funky just because it's format. If it looks a little bit confusing on how that one went, we'll delete this in a moment, but just for extra explanation, think of it as y equals negative 1/8 times x squared. There's nothing wrong with that format, but you might notice if you change the format of how you write down algebraic expressions, certain rules like chain rules, product rules, constant and multiple rules get a little bit more foggier. So differentiating this thing, just took the negative 1/8, multiplied by 2, and the new power of x was a 1. So that's what we get right there. Any questions about that so far? Yeah.
So just to clarify, it is negative x squared over 8, or is it negative x to the 2/8 power? To clarify, it.
Oh, gotcha.
Like it sounds like it's negative x squared over 8. Am I getting that correct, or is it the other way around?
It's that first way, negative x squared, then divide by 8. Yeah, exactly. And again, that's kind of a weird format with calculus, so you can visualize it this way as well if you prefer. Either way, we get here, and then it still simplifies. We have negative 1/4 x times e to the negative x squared over 8 as a power. Well, we didn't quite do it. That was just one aspect of doing this total derivative right here. So the derivative here plugs in using that result. So it'll be times a negative 1/4 x e to the power of negative x squared over 8. Well, in step 1, there's really multiple steps in step 1, if I'm being fully honest. Step 1 of step 1 is to take the derivative. The next thing to do in step 1 is to simplify the derivative. And then the final thing to do is finally tackle that equation when it's set equal to 0. So we've got the derivative here, but there's no way you want to algebraically work with that. We need to clean it up next. So going left to right, this turns into just e negative x squared over 8. Here we can combine x times x and say this is minus 1/4 of x squared e to the negative x squared over 8. And I mentioned last class, one thing that people have been doing on their papers, quizzes, and on exam settings is when you got to here, some folks factored out the greatest common factor. That's always a good call because this is the stage where we need it, the next chapter or next section as well. Greatest common factor is e negative x squared divided by 8. When you factor that out, it divides here where the red dot is, and you just get a 1. Over here, it divides out, and all that's left is minus 1/4. That was a bad parenthesis. Let me try again. Minus 1/4 x squared. So this is the derivative now in its most simplified form for what we're doing, closed interval method. Now we go to this portion, set equal to 0. There it is, and solve that equation. So we're focusing on this end. The derivative here is now set equal to 0, but because we factored, again, that's always a good call, solving the equation is a little bit faster. We're just going to split into 2 equations across that factorization. And from here, only because it's set to 0, we get to say e negative x squared over 8 equals 0, or the other factor, 1 minus 1/4, x squared equals 0. So now we boil it down to 2 different equations. There's always a hint about this one right here. You can think of it from 2 points of view. Analytically, if you were going to solve this, you would take natural log of both sides. But if you ever go to take natural log of 0, you've got a problem that's undefined. That's already enough to say no solutions on this first equation. So it's right here, kind of light, no solution. Write that small just because that one has a solution. We're not saying no solution whatsoever. But another way to think of why this has no solution is it's really based on the plot of y equals e to the x. This never hits 0 or never goes below 0. And so there's no way that that's even a possibility. You can put anything you want up in there, say square your x, still isn't going to hit 0, even if you put a negative divided by 8 or all sorts of stuff. It's an amazing fact that it will never hit 0. Keep on zooming in and you'll always find a separation here. So the moment you have a base C exponential set to 0, that's great. No solution on that one. We just move on to the next one. Any questions at the moment, folks, to this stage? Kind of amazing. We're still in step 1. This derivative is a little bit nastier to handle, but gives us good practice for the homework as well. On our next step, to solve this equation, I think the fastest way is just add negative 1/4 x squared to both sides. We'll get 1 equals positive 1/4 x squared. If you multiply both sides by 4, we'll get 4 equals x squared. Next, take the square root of both sides, and we'll have positive or negative square root of 4 equals x. So we're about ready for a conclusion in step 1. We can now say that this implies x equals negative 2, positive 2. We simplified the root and just threw the signs on it. Are the critical numbers of f. And that's pretty much the first step on optimization when we go to section 4.4, find the critical numbers. Well, now that we have it, we're still running through the closed interval method, and the next step is find the values of f on the endpoints of the interval. That's the interval right there, so negative 1 to 4. And at the critical numbers. We found 2 of them, so we need to do 4 function evaluations next. Or do we? Looking at this really carefully, here's a silly way to lose a couple points on, say, website potentially. When it said given domain, it really means this. The only valid values for x in this problem go from negative 1 to 4 inclusive. And so the moment we said that, we weren't being too careful. That one is not in domain. Only 2 is the critical number. So let's eliminate it. Let's say it's eliminated. Since it's not in negative 1, 4. So watch out for that slight issue there. That one came out to be more trickier than it looked like on paper. So there's 3 function evaluations. We need to evaluate for step 2 now. It's kind of amazing. Step 1 is like the whole page, but step 2 is short. We evaluate f at the lower end, negative 1. F at, I usually like to go in order, but you don't have to. I'll pick the critical number 2. And then after that, I'll go to the upper end, up at positive 4. But this is kind of what I was talking about with organization being important in section 4.4. Here, it's always a good idea to put in right there.
Every single one on every single flash drive.
I'm going to assume that was an open mic potentially. But we need to be very careful with this right here. And actually labeling it as f prime is a big help. Because this is not saying the derivative evaluations. It's referring to f all the way up here. So we've input information into that location. So starting off, throw a negative 1 in there, and you would get negative e to the power. Let's maybe make that a little bit easier to see. Microsoft is fighting with me. Hang on, let me get this working. There we go. Oh, that's the wrong way. Okay, I think we've got it. That's a little bit easier to see for sure. So we're plugging negative 1 inside this function, the original one. We'll have negative e to the power of. Negative 1 here is going to be just a negative 1/8. Next, we'll throw in a positive 2. Positive 2 will give us 2 e to the power of. A 2 here is going to be negative 4/8, and so that's negative 1/2. Last but not least, throw a 4 right here. We'll get 4 e to the 4 also goes here, then that's going to be a 16, negative 16/8. That's a negative 2 altogether. So we have 3 function evaluations, and that means we're just about done with the method. Any questions, folks, with getting those 3 outputs? Oh, hang on, I'm noticing the video wasn't on. That's weird. Sorry about that in Zoom. I must have been just clicking on stuff down here to try to get the audio working. The video was off for a minute, but you now see us 4 in class. So with this function here, the last step down below is really just conclusions. So step 1 is long, step 2 is pretty quick, step 3 is really rapid at this point. The largest value is the absolute maximum, and the smallest value will be the absolute minimum. But if you're like me, it's kind of hard to tell unless you think really, really hard, which one's the largest here? Not necessarily that one, and that one's not necessarily the smallest one. You can think about what happens with an exponential function with a reflection across the y-axis, or just don't forget your calculator in the exam, and that's pretty much what we're meant to do at this stage. Let's evaluate them and see what we get. So negative e to the power of negative 1/8 gives us that value. 2e to the power of negative 1/2. A lot larger, we get a positive quantity. 4e to the power of negative 2. It's a surprise, but because of the exponential function, we have a smaller value there. So this one is the minimum, and that one is the maximum. Does that make sense to folks so far? Okay, let's state our conclusions. So this one right here equals the absolute minimum, and this one is the absolute maximum. And this is a weird step to convey. I'll just put 3 there. This is our end answer for the whole method, just stating which one is a min, which one is a max. Well, any questions at all, folks, on running through this optimization? Okay, I called it an optimization problem because in a certain sense it definitely is, but it's restrictive. If we use this optimization to optimize something in section 4.4, we must have a closed set, but not every real world problem comes with a natural closed set to go along with it. So we need more tools. And that's the purpose of section 4.2. We're going to develop a first derivative test and a second derivative test for local minimums, local maximums. And then in section 4.4, we can make slight adjustments and tune those same tests for absolute minimums, absolute maximums, just like we did here, the closed interval method. So that's where the work is all going towards so far. And that was our last problem for the notes here. Any questions at all, folks, before we turn to the section 4.2? Okay, let's give this a try. 4.2, I mentioned it's a long section, and some of the problems are pretty long too, but it's not as bad as it really might sound based on that description. Because a lot of stuff you're going to see in section 4.2 are actually pretty familiar, things that we've looked at before. In fact, that's this right here. We've seen this definition and the highlighting in yellow all the way back in section 3.2. So let's remind ourselves what's going on. It says, well, by definition, this is the definition of the derivative. It's its limit definition. It's denoted by f prime. That's the limit as h goes to 0 of this difference quotient. It's a way to evaluate the slope with 1 point by limiting values. But that's the major punchline. That derivative is always equal to the slope at the tangent line at the point x that you put inside it. Because of that, we have these outcomes. If the derivative is positive, the slope is positive, but a positive slope means your function is increasing. If the derivative is negative, the function is decreasing. I left some space here just to throw in some notes, so let's illustrate this definition. In quadrant 1, let's start at value A, go to a value B, and it's a pretty basic looking function, just looks like almost a semicircle. We can say already that there's something happening right here. Let's call that a number C. And now if we pick any point on this graph, we can put down a tangent line and estimate the values. The more interesting one is right here. The slope of this one is right at 0. But that means using this definition up here, that's the slope of a tangent line that we drew. This implies f prime at c equals 0, and c is a critical number of f. Notice that that critical number corresponds to a maximum, and so we're very interested in finding those things. But there's a really big downside to all this. Finding a critical number is not enough, and that's why we have to work pretty hard in section 4.2 and even harder in section 4.4, because this is what could go wrong. You can take a function that looks like this, y equals x to the power of 5/3. Not sure if this is going to be a great one. Well, that should do the job. There is a critical number right here. There's a horizontal tangent line, a true one. Can zoom in to illustrate it's getting more and more horizontal. That means the derivative is 0 right when we put in 0 right in this location. But that is not a maximum nor a minimum. It just keeps on increasing. Right at that spot, it's settled. It stopped increasing for one instant in time if we're plotting a function against time. But it keeps on increasing right after. There's no minimums and no maximums. So critical numbers are nice, but they're not a guarantee of local mins and maximums. It's just a place to start looking. What we really need is the increasing decreasing test. If we're going to try to show if we have a critical number, it really corresponded to a min or max. So breaking this up, we can take a look from A to C. We put down a tangent line here. Tangent lines are a pretty large positive, so that means the slope is bigger than 0. But going back to the statement in yellow, the slope is the derivative. So we'll write f prime is bigger than 0. That takes us to the increasing decreasing test. F prime bigger than 0 is also conveying what we see on the graph. F is increasing. It's kind of silly to say all this because it's obvious that f is increasing when we see the graph. But when we go to nastier functions like, say, this one, we may not have a nice tool like graphs prepared for us. So we really need to use this test verbatim to see if we have a minimum or a maximum. And likewise, just to finish this off, from here to here, put down a red and tangent line like before. That one has a negative slope. And so that means the derivative f prime will be negative from C to B, excluding C and excluding B, just in the open set. And f is decreasing. So this is the analysis, and it's the reason why we have the increasing decreasing test. Well, it's more about finding that maximum that we saw in that picture there. Well, any questions at all, folks, with the new test right here and the illustration? Okay, well, let's put this to good use. It's one thing to see how it works on the graph, and entirely another thing to do it analytically, where there's no graph at all. But when you do these homework questions, keep in mind you can always double check your work, get intuition by just plotting the function. And that's what we're going to do once we finish off this process. We'll see if we're close or not. So we have a degree 3 polynomial. If it was degree 2, you could have just used, say, the vertex formula for maxes and mins. Fun fact, that vertex formula comes from all this stuff in calculus. You can prove it using these methods. But now we're going to do it something that doesn't have a vertex formula, the degree 3 polynomial. We want to find intervals where f is increasing and where f is decreasing. If we can do that, we'll combine our work with the first derivative test, and it says, if the derivative changes from positive to negative at your critical number, you have a local maximum. The reason that works is the derivative is telling us whether your function is increasing. If f prime is positive, you're increasing here. And if it goes to negative at C, you're decreasing. And so the picture would look like this. You have a local maximum in that scenario. Now for the version down below, if f prime changes from negative Where it's negative, you're decreasing, so the curve is going to look like this. To positive, now it's increasing. Let me fix that there before I get too far. Oh, and let me try to also draw that appropriately. If f prime changes from negative, meaning it's decreasing, and I drew that the wrong way, that's a decreasing curve now, to positive, making it increasing, then right down here would be your local minimum below. So that's the logic of the first derivative test. And for a lot of these tests, both the first derivative test and the second derivative test, there's a possibility of a failure at your critical number. If it does not change sign, then you have neither a local minimum nor a local maximum. And that's exactly what's going on with this graph right here. The derivative stays positive, it goes zero, but then it goes back to positive. That's what we mean by it didn't change sign. And so no mins or maximums in this case. So here's where the test fails. Well, not necessarily, it just means we didn't find a maximum nor a minimum value to that function. Well, to get any of this started, what we need is a critical number, because if we're trying to see where the derivative changes from positive to negative, that happens exactly where the derivative is zero itself. So once again, it's all about the critical number. It could also happen where the derivative fails to exist, but those are kind of rare fringe cases. Well, let's give this a try then. We have a degree 3 polynomial, and for step 1, to find where it's increasing and decreasing, you immediately just differentiate it. Kind of like the problem we started out with today. So f prime of x to start. Down the line, this is going to be 6x squared minus 18x plus 12. Constant will fall off, and now we have our first derivative. We need to set that to 0 and solve it. And just like before, we shouldn't settle for that. Let's start simplifying it down. You can start by factoring out a 6. That'll leave an x squared minus a 3x plus a 2. Now this one has to factor further. I will make one deal with you for sure though. If we're doing an actual real exam problem, that is always going to factor nice. I'm not going to throw a quadratic formula at you. It's just kind of a weird thing to do in a timed exam. There is a possibility you could use a quadratic formula here on an actual homework question, but I don't think I went for those either. So usually these are going to factor pretty quickly. In this kind of way, trial and error should do the job for us. Split up x squared as x by x. Negative here with a positive means both signs are negative. And factor 2, it's prime, so my best good bet is a 2 and a 1. And then just double check in this way. Here to here is negative x. Here to here is negative 2x. And we did get to negative 3x as intended. So that's the factorization step. And just like on the first problem of the day, oftentimes if you're solving that equation, something set equal to 0, you're probably wanting to factor it. Because once it's factored, setting it equal to 0 gives you immediate solutions. This will imply x equals 2 or x equals 1 are the critical numbers. Of f. You don't have to write out are the critical numbers of f, but I've been doing that as a habit in the notes just to signify that's one of the major portions of the work. Without getting that one step just right, everything else is going to look pretty funky and be just quite a bit off potentially. Any questions at all, folks, on how we got the 2 and the 1? Okay, now this is kind of the, how should we put this? This is the step where it's easy to kind of lose our way. This is something that will be expected to do in a real exam setting, so I encourage you to also do this on quizzes as well. If we want to see where it changes sign from positive to negative, what we really need is a sign chart. There's a couple ways to do this. One way is just write down a number line. I like to put infinity here and negative infinity here to help with what we're going to do. Our answer is going to be intervals in interval notation. So next, grab your critical numbers just found and drop them in. So we'll go 1 and a 2. Next, I'll usually like to put little brackets here just to organize which regions we're looking at. So I have an entire open set that goes from negative infinity up to 1. We need the sign of the derivative there, here, and here. At this point, we're really just testing values. Let's use a different color for that. So we just need one piece of information here to determine the complete sign of f prime, because what we know about f prime is it's 0 here and nowhere else. That means if it's positive for one number in this region, it's positive for every number in this region, and same with negative. All we need is a test value. And the easiest one in this case would be a 0. I've honestly made a mistake where I picked a number between 1 and 2 that is not between 1 and 2, so don't make the same mistake I've made in the past. 1.5 is a good candidate here. 1.1 would work. Just has to be between 1 and 2. We can't pick 1 either because we already know if you throw in a 1, the derivative is 0. We have that information. Over here, you could get fancy and put in 1,000, 20, or just a 3 would do the job. And those are going to be our test values. We'll use them to resolve the sign of f prime on all 3 of those regions. Does that make sense to folks so far? Okay, so now let's put into action what we set out to do here. Calculate f prime at 0. That means we go to the derivative, which is right here. It's easier to use in its factored form because we don't need to know the exact value. We're just plugging in an x and finding a sign. We'll get 6, -2, -1 by putting zeros in for those x's. Everything is still multiplied, but that comes out as a positive value. So I'll put here greater than 0. So now already we have some great information. If the derivative is bigger than 0 here, it also means it was increasing in that region. Actually, let me use a slightly different color. So it's increasing in that region. Oh, sorry, I take that back. I'm realizing my color coding is going to break down. I'll just go with purple. Color coding is no good if it becomes confusing or a conflict. So we're increasing here. My guess is it's going to be decreasing here. If the powers on these symbols or groupings are 1, it really will switch. So this is a dangerous shortcut, but let's take it just to illustrate how it could work if you like it. I'm anticipating that's going to go negative, and so decreasing. This will go positive, so increasing. And the only way that pattern ever breaks down is if you have something like this. I'll delete it in a moment. An even power breaks that pattern. It would cause this to match signs if it was even. But if all the powers are odd, and they are, their power is 1, your signs will always alternate in this nice predictable way. But because that's a dangerous step, if you have extra time in an exam setting, it might not be a bad idea to just double check it after all. So f prime at 1.5 means for 1.5 up here where the x's are, be 6 times -0.5, and over here it'll be a positive 0.5. And that's just one negative sign amongst 3 factors, so we do in fact have negative right here. Then one last try, f at 3. Excuse me, f prime at 3. It's really important we say f prime. So the derivative, f prime at 3, is going to give us 6 times 3 minus a 2, so a 1. 3 minus a 1 over here, so a 2. And we have another positive value in that location. So it does indeed go increasing, decreasing, increasing. And here's where the first derivative test takes over. If f prime changes from increasing to decreasing, you have a local maximum. So we're expecting a local maximum here. If it changes from negative to positive, there's negative to positive, we expect a local minimum. But for the moment, we also just wanted to know the intervals where it was increasing and decreasing. And so this is the first part of the answer. F, well, let's maybe call this a step 3. Step 2 is the large step on this one, analyzing the sign chart. And now we can say F is increasing on negative infinity up to 1 as an interval. It would look like this. Then union, the set, increasing here as well. It goes from 2 to infinity. I notice we're using parentheses on all of these things, not just because of the infinities, it's also because right at 1, the function is neither considered to be increasing nor decreasing. That's a point of where it hit a maximum. We think of it at rest at that point. Same for the one over here. So we have the increasing, and now we can say, and is decreasing on the open interval from 1 to 2. So we did it, folks. We've analyzed the nature of the function. Based on just the derivative itself, you can tell exactly where this random third-degree polynomial increases and where it decreases. But the larger question is not so much what we did here in step 3. The larger question, and the reason why we would do anything right here with the increasing-decreasing test, is because we really want to use the first derivative test. We're more interested in local maximums and local minimums. And so let's apply it right here in part B. Any questions at all so far, folks, with the conclusion in part A? Okay, so it says find the local minimum and maximum values of f. This is dangerous because that is not f. We have to go back to the original function. I should have copied that as well. Okay, let's drop that in, and I think we can get started right here. I want to have a sign chart to help out the original function, and this helps out as well. So it says your function is increasing, and then it went to decreasing right at 1. In other words, if I was to sketch the graph right at 1, it would look about like that. I'll delete it in a moment since I don't want the diagram to get too busy, but that's got to be a local maximum. So we'll say f at, we input the critical number 1, which means we are valuing the original function down below here to get 2 times 1 minus 9 times 1 plus 12 times 1 minus 3. And it comes out as, let's see, 2 minus 9. Well, this is a lot of stuff. That looks like negative 9 plus 9, so a value of 2. And that is a local max. And we'll definitely double check it. There's so many steps going on here that if you're doing this as a homework question or a quiz question, definitely take advantage of technology. Graphing calculators can really help out a lot when you're learning this kind of stuff. So we have a local maximum, then at 2, let's see what happens. It went decreasing and then increasing. And so my picture is not quite right, but that means you'd have a local minimum. So let's write out f at the next critical number 2, which is going to be equal to, now we're inputting 2 into this function. So it'll be 2 times 2 cubed. So that's 2 times 8 minus 9 times 2 squared. So minus 9 by 4 plus 12 times 2 minus 3. And this is the moment in time where we say, we've worked really hard this semester. Definitely take advantage of a calculator. The emphasis is the calculus, not so much the arithmetic. So let's just throw that in. 2 by 8 minus 9 by 4 plus 12 by 2 minus 3. We get exactly a 1 out of all that. And that 1, like we mentioned, is a local minimum. So we did it, folks. This is optimization. We grabbed a random cubic polynomial. We can't even use the vertex formula on that for the quadratics. Yet, without even looking at the graph, this is my claim. We have a maximum and a minimum, and these are where they occur. They're local, but not global. Well, before putting in an answer like this one in, or maybe say, better said, before setting in a quiz, definitely check it out. Let me clean this up just a little bit. And let's throw this into Desmos and just see how close we are to all this stuff. We're also going to reuse this graph, so good opportunity to take a look at the next concept with it. It's f of x equals 2x cubed minus 9x squared plus 12x minus 3. And we need a better window than this. Interesting values happened at, we said, 1 and 2. And yeah, right at 1, if I could point to that, at 1, we have, next try, there we go. We have a local maximum of a height 2. If we put in 2, we have a local minimum at height 1. And that's exactly what we were saying down below there. So we did it, folks. This is the rundown of the increasing, decreasing test, as well as the first derivative test for optimization. Any questions at all, folks, with our work here? Okay, let's capture this graph because we have a cause to use it again. And the next course of action is issues about concavity. Concavity is kind of a tricky definition, but when you define it the first time, it's all about tangent lines. Next, after we go through the tangent line definition of it, the good news about concavity, it's hard to conceptualize, but it's really easy to test. It's just a second derivative test, or better just said, the concavity test, where you use a second derivative. If your second derivative is positive, you're concave upward. If your second derivative is negative, you're concave downward. And you couldn't ask for a better description than that, because this test down below is kind of bonkers in a way. Positive here does correspond to a local minimum. Negative here corresponds to a local maximum. That just feels like a typo. So there's some weird things going on with concavity together with the second derivative test, which means we need to spend a good amount of time right here and say, what in the world did we even mean by concavity? Concave up versus concave down. So let's start off. We'll say the graph, we'll say if the graph lies above all of its tangent lines on some range or some interval, it is concave up. So if we start drawing tangent lines, let's do one right here. Notice that the graph in black does lie above that horizontal tangent line. That means in a certain region around 2, it would be concave up. But if you look at this location right here, let's read out this definition. Likewise, if the graph lies below all of its tangent lines on an interval, it's concave down. So we'll draw a tangent line. The horizontal one is just the easiest one to draw. It's the only reason I've been putting it on there. And notice in this range, right around 1, it's concave down. The graph is below the tangent lines. That means something weird has happened between 1 and 2. Somewhere on the graph is a transition point where we went from concave down, the curve is below, to concave up, the curve is above the tangent line. That transition point is referred to as an inflection point on the graph. So if we can find the inflection point, we'll know the range where it's concave down, concave up. And this is the part where it is pretty tricky to give this a try. This is one of the reasons in WebAssign I put like 100 attempts on questions that involve these kinds of graphs, because it's honestly pretty tricky. What we need are even more tangent lines to make this happen. Over here, if we go to the left and start putting down tangent lines, it'll start looking like this. It looks like anywhere we put a tangent line, the curve is going to lie below it. So now we're going over to the right and doing kind of the same sort of experiment. For tangent line right here, it looks to me like it's still going to be below, but right around here, I honestly wouldn't be sure. It's kind of hard to tell. Let's take it from this side. On this range, or excuse me, on this interval, we are concave up. The curve is above its tangents. If I put another tangent out here, it appears it's going to stay concave up as we go out in this range. But somewhere out here, they get hard to draw. Right around here, I think I can still attempt a tangent line that looks believable. I would say in this location, the curve is still above that tangent, but I'm rapidly losing the ability to discern concave up versus concave down somewhere in the middle. So that means somewhere in the middle, we have an honest point of inflection. It'll happen at some number C, and the inflection point is at C, comma, F at C. So that's our point right there, where we transition from on the left let's go through it again. Somewhere up to C, I'll draw it this way. The graph is below all those green tangent lines, which means concave down. But then when we went to the right across C, the graph, oh, and let me change the color as well. When we go to the right across C, the graph is now above tangent lines, and so we'll say it's concave up. And C, well, that's the x-coordinate to the point of inflection. But one word of warning, when it says inflection point, it really means we have to give the full point. That'll be more obvious in WebAssign because you'll know you're putting an x-coordinate and a y-coordinate, but that becomes easy to miss on a quiz or exam setting. So let's make an emphasis here. The answer is a full ordered pair, an XY coordinates, in other words, that we would have to give for an inflection point. On a real exam, if you did give me that part, that's not a big deal, honestly. I'd probably take off a point, nothing major. But you could lose the question on, say, WebAssign, and it can be frustrating if you're not sure why we're missing it and we have the right C value. Well, we did it, folks. That's, well, the definition for concavity. Any questions at all, folks, on determining concavity, just visually? Okay, one thing I want to mention, just a bit of a preview of the second derivative test that we'll take a look at when we come back on Monday. Notice when we said concave down, we look at that, that's a local maximum, and that really hurts my head whenever directionalities are reversed. Concave down means maximum. This is concave up, and that corresponds to local minimum. Again, that's always unfortunate when math does that to us, but sometimes directionalities are in conflict with this kind of stuff. So that's determining concavity visually. Analytically, if you have to find concavity, this is the test to make it happen. And again, it's quite a nice test in a certain sense. If the second derivative is positive, that's concave upward. And if it's negative, that's concave downward. Now, when we go through this problem, one thing to keep in mind, in fact, let's put a remark here because it is kind of a remarkable observation to make that can help. The process we take here in example 1 for concavity is highly similar to the process in example 1 for local minimums and maximums. So we're not necessarily doing anything too different, really. For example, we are still going to take a derivative. We'll happen to take the second derivative and solve the second derivative. We still do a sign chart, but these are all second derivative values. Then we just say where it's concave up, concave down. Instead of giving local maximums, minimums, we'll just give the inflection points, however many there were. So that's going to be the process on this one. And when we come back on Monday, I have another do-over where it's going to be everything all at once. So this one is a little bit more of a challenge, but just meant to help with the homework. But first, let's give this one a try. I think we've got just enough time to make it happen. Yeah, go ahead. Oh, I must have. Thanks for spotting that. The process we take here is, yeah, I should have said example 2 right in there. Thanks for spotting that. Other questions so far or comments? Okay, I think we're ready to give this a try. Let's call this the final question of the night. These, again, sometimes turn into pretty long problems, but the more we organize, the better we're able to navigate through everything. So we start with the original function f of x. Let's blow it up just to make it more apparent. In the concavity test, we first, as a step 1, calculate f prime of x. That's not so bad. It's a chain rule, but this is a logarithm, and we did this problem right before spring break. So we'll take our time with this one as well. This one's also a chain rule process where the x power 4 plus 27, that'll be derivative 2, the inner function. The inner function is usually easier to spot. It goes inside something. And so the outer function on this one is the natural log. So when we go to calculate f prime of x, what the derivative is, derivative of natural log x goes 1 over x. So we just put down our input in the denominator. But then because it's a chain rule, we'll multiply by the derivative. It multiplies cleanly right into the numerator like that. So every kind of formula like this, or function like this, chain rule always boils down to this situation. Take the inner function, copy it to the denominator, copy it into the numerator where we will differentiate it, and we're just about there. In the denominator, I'll just draw parentheses, x power 4 plus 27. In the numerator, we get 4x cubed. And now we did it, folks. That's our step 1. Not too bad so far. Now for step 2, here, well, the first derivative wasn't too bad to calculate because it started out as a logarithm. That was just a fast chain rule. But now the second rule is turning into a quotient rule, so we need to be really careful with this one. So let's write out f double prime of x. Been a hot minute since we've done the quotient rule, so let me write down the pattern. You would differentiate the top, 4x cubed, and then copy the denominator, x power 4 plus 27. Then there's a minus in the quotient rule. For me, that's my easiest mistake I make right there. I'm used to using product rule, I suppose. Copy the numerator, 4x cubed. Differentiate the denominator, x power 4 plus 27 prime. And divide by that same denominator, x power 4 plus 27. But don't forget to bump the power to power 2. That's the second most likely mistake that I personally make on quotient rule problems. Okay, now that we've got the format, it's all just a little bit more calculus and a lot more algebra to simplify this down. Starting out over here, we have 12x squared, multiplying x power 4 plus 27, minus, over here, 4x cubed, multiplying 4x cubed again. It's kind of nice in a way. Whole thing is still divided by x power 4 plus 27 squared. And it continues. So now we're distributing. I'm sensing the need for a calculator on this. I need a 12 by 27 at some point. Okay, 324. I'll try to remember that. So distribute 12x squared through, and you'll get 12x power 6. And then when it multiplies here, we get plus 324 x to the power of 2 altogether. That takes care of the distribution. Over here, nothing fancy, we get negative 16 x to the power of 6. Then carrying down that denominator, we have x power 4 plus 27 squared. It's definitely tedious, I have to admit to you, to copy a denominator repeatedly when it never changes. But sometimes if you neglect to copy it once, you could forget it's even in the problem. It's happened before. So let's keep on going. I'll start with 324x squared. Now we have 12x power 6 minus 16x power 6 for a negative 4 x power 6. X power 4 plus 27 squared. And we've done it, folks. This is the second derivative. Now, taking a look at the test, notice it's saying f double prime bigger than 0 or f double prime less than 0 for concave up, concave down. That means what you're doing in step 3 is we have to solve f double prime of x equals 0. In other words, we're doing a critical number. Our author doesn't mention it because it'd be confusing. It's the critical number to f prime, not to the original function f, since we're solving the second derivative set to 0. But a better way to think about it is we're just trying to solve inequalities. And to solve any kind of inequality like that, well, you need to set it equal to 0 and find where it's 0 first before you find where it's positive or negative. Now, one thing we did mention is if you set a fraction to 0, the only possible way you're going to get an outcome is if the numerator, 324x squared minus 4x power 6 itself is equal to 0. Looking at the denominator, there's no way it's ever undefined because x power 4 is at minimum 0. So the whole thing is at minimum of 27 squared. Only issues are going to be where this thing right here goes to a 0. So let's start solving this thing. Factoring is our go-to method, and we can factor out a 4x squared to start. I'm hoping 4 divides into that. Let's double check that. 324 divide by 4 goes in a nice clean 81 times. So we get 81 here minus x to the power 4 set to 0. So that's the factoring step. Well, it's the start of the factoring step. This continues to factor. This one is now a difference of squares. This is 9 times 9, x squared times x squared. So it turns into a 4x squared times 9 plus x squared times 9 minus x squared. And that's our difference of squared formula in action right there. Then sometimes factoring is an adventure. This one is done. This one is an irreducible polynomial. A sum of squares will not factor unless you use complex numbers, but we're avoiding those entirely. And that one's another difference of squares, so it does factor. So on the next line, we've got 4x squared, 9 plus x squared, and this one splits as 3 plus x times 3 minus x, all set to 0. So now we're definitely in a better shape. Let's get our critical numbers. Going left to right on this factor, we'll say x equals 0. That's the only solution on that one. But note, that has multiplicity too. That will affect our sign chart, and if we abuse that information right there, you could do a sign chart really pretty rapidly on this. On this one, there is no 0 whatsoever. We're looking for real valued zeros, and there's no way to get a 0 here with 9 plus x squared. If we move over to the next, that'll be a negative 3. For this one, we have to put in a positive 3. And both of these have multiplicity 1, because the power here was 1 and 1. So from then on out, we're about ready to do a sign chart to finish off the problem. Any questions, folks, with part 3? I think this is kind of the algebraically oppressive portion of the problem. Okay, well, now we need the concavity test, so let's just take a quick screenshot. I was drawing on it. Okay, so the next thing we're doing is, again, this is the reminder, this is very highly similar to what we did in example 1. We have a step 1, 2, 3, and now for step 4, we throw in a sign chart. This is pretty much it though. Once we resolve the sign chart, all we're going to do is state our conclusions, where it's concave up, or it's concave down. And let's also not forget this portion. We also want the inflection points on the graph. I'm going to copy that because I have a feeling I'm going to forget that. Okay, so just so it's there, I've got it posted down below. Now, the only thing we do with these values is we throw them down in the sign chart. We have a value of 0, negative 3, positive 3. But that means with 3 cuts, we have 4 different regions we have to test. Let's start with putting down, like we did before, f double prime. Our whole goal is to determine if this is a positive or negative. Now, that means we need to grab our f double prime. Let's see where it is. It's right here, but that's not its best format. Let's rewrite it. F double prime of x. Let me find a better spot to rewrite it. I have to zoom out just a touch temporarily. F double prime of x is now equal to, in this numerator, we factored it down to this. It's actually a little bit easier to navigate the sign chart if we're using the factored form. So I'm going to put down 4x squared, 9 plus x squared, 3 plus x, 3 minus x, and then it's divided by that portion, x power 4 plus 27. Squared. Okay, so we've got our second derivative pulled down as well. We need that because we're doing a sign chart based off this function right here. So good idea to collect it in one spot. Now we need to find some test values. And oh, that's not the way to do it. Let me Control Z and head out. I'd say good choice here is a -4, then maybe a -1, +1, and maybe a +4. That's a lot of stuff to check. But another thing to keep in mind is the only parts of f double prime that can change signs are, let's take a look. 4x squared, always positive. So you have to wonder, do we need to put anything in there? If it's always positive, that's a foregone conclusion. 9 plus x squared is always positive, but this one can change. Throw in -10, you've got negative. Throw in 2, you've got positive. So 3 plus x is important. Likewise, 3 minus x can change signs. But down in the denominator, due to the power 2 already, it's always positive, and it's definitely always positive because the inner function is also always positive. So if we're doing a sign chart, sometimes it's a good idea to just focus on these elements right here, because that's where all the action is. That's where the signs could change. Everything else is always positive. So here's how we're going to run through, not like that. Here's how I'm going to run through doing the sign chart next. We'll pick it a x equals -4, take that -4, and as opposed to throwing it into the entire function, which looks like a whole bunch of busy work, that's terrible, just put it right here. You would get 3 minus 4, so -1, multiply 3 minus a -4, so that's 3 plus 4 for a 7. And that's negative. So up here it tells us the second derivative is negative, and that's concave down by our concavity test. Now we have to keep on doing it, but if you're thinking about multiplicities, let me show you what the shortcut would be. You still have to test one region to get it all started. Now look at the critical number at -3. It's relative to multiplicity 1, which is odd. That means I'm anticipating a sign change. No, I didn't do it. Let me try again. F double prime should be bigger than 0. But now we have to be really careful. Go to the next critical number at 0. At 0, we had multiplicity 2, which is even. That means no swap. It should stay positive relative to 0. Then on the next region, carefully check 3 came from here, which is multiplicity 1. So back over here, I'm expecting a flip. F double prime should be less than 0. So my claim is that's the correct sign chart. That's an acceptable thing to do on any kind of work you're doing, quizzes, homework, exams. But in an exam setting, if you have extra time, it is still a good idea to check these out. So let's take a look. X equals -1 means we're plugging -1 into these locations. That would give us a 2 and a 4. That's positive, so it matches with positive here. Now let's do it again. Throw in a +1. These are the only things that can flip signs. This will be a 4. 3 minus 1, so a 2. And sure enough, take a look at that. It's positive, and really the only reason it's positive is because of that, a power 2 right there. That was x to power 3, x to power 7, or just an x. This would have flipped to negative. It's kind of remarkable in a way. Now, last one at 4. We're plugging 4 down here, and that'll give us a 7. 3 minus 4 will give us a -1. And so that one did flip signs. It went to negative right here. That's a lot of work, but we're getting through it, folks. That's our completed sign chart. Let me take this right here. Now we're going to use the concavity test to just give our conclusions to everything we see. So starting off, where it's less than 0, we have concave downward. So we can begin by saying F is concave down on, I'll give this as interval notation since that's expectation Webb assigned. It goes from -infinity to -3. Actually, let me write it down here so we're not squeezing things too much. So that's our first negative sign. Then skip all the way to this one, union 3 to infinity. And is concave up on, well, this one's kind of tricky in a way. I think the reason I like this question is it's a technicality in a certain sense. Right at 0, if we were doing an example 1 problem, that would not be increasing nor decreasing. It's a local min or max. But for a concavity problem, there is no concavity right at 0. Concavity means positive for the derivative, but at 0, the derivative was 0 for second derivative. So when we go to write our answer, if you wrote -3 all the way to 3, I wouldn't take off a point on that. But Webb assigned will, I'd probably just make a comment on your paper. It's concave up on -3, 0 with open parentheses, union 0 to 3. In other words, right at 0, there is no concavity, and it didn't even change in concavity to the left or to the right. So that's not even an inflection point that we're looking at. Well, that's the conclusion of the concavity test so far. Next thing we want to find are the points of inflection. But any questions at all, folks, on resolving concavity? Okay, if you like organizing these things a little bit better, you could also write out this on your sign chart. I put increasing, decreasing on the example 1 problem. Here you might say CCD for concave down, CCD for concave down, CCU for concave up, CCU for concave up. Just as a shorthand, it's not required, but it might be helpful to take this to convey what you're about to write down below. It's also helpful for finding inflection points. We're just looking at the concavity a little bit more closely over here. Now recall, an inflection point is a point on the graph where concavity changes. So when it says inflection points, or points of inflection, we're going to have one when x is 3, or excuse me, -3, and one when x is +3, because we switch concavity here to here, but no inflection on that location. The other thing that's tricky is when it says inflection point, it really looks like this. The inflection points are, we take the -3 and evaluate f at -3 and scroll for just a touch. And we do the same for the other value right here, +3, and evaluate f at +3. But this is suddenly extremely tricky because there are 3 functions on the table now. There's the second derivative right here in purple. There's the first derivative right here in black. And when it comes to inflection points, they are points on the graph of f, which means we return to the original function. Much like with local minimums and maximums, we always go back to the original. So let's drop it down here just for a reference and plug this in. I'm sensing the need of another calculator, so let's also grab Desmos. And we need to put in 3, -3 inside here and increase by 27. Because the power is even, it actually doesn't matter if you throw in the negative or not. It's going to be the same quantity. -3 power 4 plus 27 gives us 108. And so that's the natural log of 108 here, and same right here. So our inflection points go -3, natural log of 108, +3, and natural log of 108. What we did, folks, I'm just double checking the numbers there. That's the full run through whenever we're dealing with concavity and inflection points. A lot of work on these kinds of things, but any questions at all, folks, with this stage of the process? Okay, well, I appreciate everyone's work on this. This is definitely kind of tricky stuff. It's kind of weird. In chapter 3, the major thing we're fighting is technical derivatives we have to calculate. But now in chapter 4, the major skill is doing a long analysis that could start with a mistake here influencing the whole process. So this is another style of doing mathematics in a certain sense. When we come back from the weekend, we'll take a look and review both of these processes with example 3. We want everything, local minimums, local maximums, and inflection points as well. And then right before going into the next section on optimization, we'll take a look at what's happening with the second derivative test and optimize a new problem with it. After that, we'll be into the applied problems in chapter 4. Well, that's all I have for folks today. If you have any questions, I'll be happy to help out. Otherwise, have a great weekend, folks. If you have any questions while you're working problems or studying material, don't hesitate to email. I'll be happy to help out. I do understand these are longer. I'm almost expecting questions over email. Have a great one, folks.